Hi, my name is Chi-Wei. I'm now presenting our work, Specialized and Fused, Pyramidal Output Representation for Semantic Segmentation. This work is in collaboration with Chen Sun, Huan Zhongchen, and Ming Sun. Given an RGB image, the goal of semantic segmentation is to predict the per-pixel semantic map. Usually, people train their neural networks to predict a single finite scale semantic map. On the contrary, this work proposes a multiple semantic output representation as the training target. We first explain the motivation behind our output representation. So this is a standard finite scale semantic map. If we take a closer look, we will see that many large image cells, or image patches, contain only one semantic label. Representing such an image cell with a single label will not introduce any loss. On the other hand, the other cells still contain multiple semantic labels, and thus cannot be fully represented at this scale. Therefore, we need to break them down into finer cells. Again, in the finer scale, we can see many cells contain only a single semantic label. So, if we repeat such a process until the finite scale, we can derive a lossless output representation, which uses less labels to represent all pixels without any loss. Next, we explain the proposed output representation. In this work, we use mixed cell to refer to a cell which contains pixels of different classes. And we use unity cell to denote a cell where all pixels share a single class. Intuitively, in our output representation, we decompose a per-pixel semantic map into 4 different scales, and each of them is only responsible for a subset of pixels. We train a neural network to predict such an output representation, and in the inference phase, we acquire the semantic labels from coarse to fine, and fuse them into a final semantic map. In more detail, the cells in chromatic colors are the unity cells, and their semantic labels can fully represent the underlying pixels. And the black cells are the mixed cells, where the semantic labels are invalid. And the gray cells are done by cursor, which means that they are unity cells but already done in the cursor scales. The semantic labels at mixed cell and done by cursor cell will not be used in the final prediction, and will also be treated as don't care in the training phase. So, each of the 4 predictions are trained to only focus on the pixel they are assigned to. We will show later that, in this way, the output at each scale can have its own specialization, and thus the final fused prediction can become better. Let's see how our output representation actually works. Our model will predict a unity pyramid, which classifies whether a cell is a unity cell or a mixed cell at different pyramid scales. As we assume that all cells at a finite scale to be unity cell, there are only 3 scales in our unity pyramid. Our model will also predict a semantic pyramid, which predicts semantic segmentation at 4 pyramid scales. We can see that the quality of each individual row semantic prediction are bad. This is because they are trained to focus on a small portion of cells. Our post-processing step will take the prediction only if the pyramid scale is specialized to it. The first step is to mark all cells that are covered by a unity cell at any cursor levels as done by cursor in the unity pyramid. Then, in both training and inference phase, we ignore the semantic predictions of all mixed cells and done by cursor cells. Finally, we simply resize the 4 post-processed semantic prediction and sum them together to form the final prediction. Next, we show our network architecture for the proposed output representation. On top of the backbone network pre-trained on the ImageNet, we add a semantic hash for predicting semantic pyramid, and the unity hash for predicting unity pyramid. The unity hash is simply composed of an average pooling and shallow convolution layers. The semantic pyramid can also be generated with a simple semantic head, where the feature from backbone is pooled to multiple scales. Then we use 2 1x1 convolution layers to generate the semantic output for each level. Besides the simple version of semantic head, we further designed a coarse-to-fine contextual module, where intuitively, the information from a cursor level is passed to finer levels by updating a small context feature. Next, we show the results and analysis. The proposed output representation constantly shows improvement under different network architectures. As mentioned earlier, it is important to treat done by cursor cells as don't care to enable the finer levels to have specialization. Without this design, the proposed output representation cannot bring any benefits. On the contrary, Our representation with the don't care relabeling demonstrates a clear improvement. As can be seen, the proposed contextual module, which is tailored for our semantic pyramid output, outperforms the other baseline architectures. Interestingly, we find that different pyramid scales are specialized in different classes. For example, the traffic light is better predicted at the finite scale. We also show that each scale of our semantic pyramid is particularly good at those pixels assigned to it by the unity pyramid. We experimented with ResNet 101 backbone and HRNet 48 backbone, and we report our results on ADE20K dataset, ADE20K official evaluation, Cocoa Stuff, and Pascal context. Our method is better than or on par with the recent works. Finally, here are some qualitative examples. Thank you and have a nice day.